Hi, everyone. I'm Susan Nash, AEPG. It's a nice rainy day here in Tulsa, beautiful Tulsa, and the rain is beautiful. And we have a fantastic talk today. We'll be recording it too in case people are not able to see it in person or live. It's a very important talk. A lot of people are using this technology now. It's X-ray fluorescence based on elemental analysis and identification of reservoir and non-reservoir intervals in organic rich mudrocks. And we have Jim Puckette of OSU here today. And I'm hoping that he might be participating at your tech on this topic too, because I think it's something that is incredibly important, especially now as we're trying to optimize the reservoirs and then design refracts, et cetera. But at any rate, thank you, Jim, and just welcome.
All right. Well, I'm sitting in our core facility, the Gary S. Stewart Core Research Facility at OSU. I'm the only one in our little building out here. It's very quiet. It's a good place to be. And we've enjoyed rain today as well, and very welcome rain. So what I'm going to talk about today is some work that's been going on for some time. You're going to see I'll talk about some of the collaborators here in just a second. You're going to see some student names, but I'm going to focus mostly, well, I am going to focus in this presentation, on the Woodford Shale and the Caney Shale. And we have an ongoing project with the Department of Energy, and you can see the DE, whatever it is, FE 31776, field evaluation of the Caney Shale as an emerging conventional play in southern Oklahoma. So this is it's been a 4-year plus research project. And our collaborators on this project are many. Obviously, I'm at the Boone Pickens School of Geology, but our folks over in chemical engineering, which hosts the petroleum engineering folks here at OSU, we have a master's and a PhD in petroleum engineering under that chemical engineering umbrella. And Maleba Radanji has been leading that team. And we have, of course, the Department of Energy, Fossil Energy, the Berkeley Lab, LBNL. Joe Rink is our program officer, for those of you who deal with DOE a lot. Andrew Bunger is engineer up at the University of Pittsburgh. And Dustin Crandall over at NETL has been involved in the project. And Abbas Dalali down at the Oklahoma Geological Survey, he's no longer there. He's gone back into industry and is now, I believe, in Houston. But they're a part of our team. And then in the School of Geology, I really want to acknowledge Dr. Yulin Wong and Dr. Jack Passion, I call him Jack, and Mike Grammer, carbonate expert. And these are some of our students over here on the right that have worked on the project. Some are undergrads, some are MS degrees. But anyway, it's a big project, and it's been a fun project. So this the slide that you see right now is kind of one of our geologic workflow slides that we use up here on reservoir characterization, and I attribute this slide to Mike Grammer. But for those of you who are involved in exploration or in reservoir characterization in general, these are some of the things we work with. And starting out with, in some cases, seismic. We work at the log scale, we work at the core and thin section scale, we do regional mapping, regional cross sections, and then we get down to the nanoscale and micro scale, try to tie petrophysical properties to the rock. And we do mechanical properties as well. Here's a little rebound hardness test tool, and evaluate fracture aperture and size and frequency. And my area in particular in this one project, I'm more involved in stratigraphy and reservoir mapping. Of course, I come out of industry, and came back to academia after a number of years trying to find oil and gas. As I said, I've drilled lots of dry holes, but that's part of the business. We are using X-ray fluorescence today in this part of the study. And I'm going to talk about how we take XRF data and apply it, in this case, to recognizing reservoir intervals that are basically have a lower clay content, and how we use different elements to detect that, compared to more ductile intervals that have a higher clay content. And even though those more ductile intervals contain porosity, trying to get them to fracture is very difficult. So we call them ductile intervals or non-reservoir intervals. I don't know much about XRF. I'm not a chemist, but as much for me or as anybody else that's on the presentation today, this is a diagram borrowed from Thermo Fisher. We use a Thermo Fisher handheld instrument, and some of the data you see today, we also had a survey done by NETL, Dustin Crandall's group. But you're going to see a lot of Niton, Thermo Fisher's tool. You'll see a lot of that data today. So what happens is we take this instrument and we apply radiation, put the instrument up next to the rock and generate radiation. Goes into the rock, right into the very surface of the rock, actually. And this radiation causes electrons from the lower shells to be ejected. And some of these outer shell electrons want to drop into those lower energy levels. And to do that, they have to shed energy. And when they do that, they emit an X-ray. And these X-rays are characteristic of the element that we're looking for, or the series of elements we're looking for. And the tool works really well in sedimentary rocks. And I will emphasize this right now, that we're using it in a qualitative sense. If we wanted to do quantitative work with it, we could, if we did a lot of repeat measurements and made sure that we corrected the data for the standards. But what I'm presenting today is qualitative, and it's a change in the concentration of certain elements from one interval to the other. So this is our introduction to XRF. And now let's go out and look at some of the work that we've done. And I'm going to start with the Woodford. I would never have said that the Woodford was easy until I've looked at some of these other shales. And for those of you who know anything about Oklahoma geology or have followed Woodford development in Oklahoma, this is one of Brian Cardot's images from a presentation and a publication. It's from 2014. And it just shows the Woodford development in Oklahoma over time. And I'm going to show some data down here from the Scoop area. And those of you who have worked the Woodford know that as you move towards southern Oklahoma, the Woodford becomes very cherty. And later on in the presentation, I'll show you an outcrop photo of the most famous Woodford outcrop in the world. And that's the Woodford outcrop on the west side of I-35 in the southbound lane. And when we look at the Woodford, we find that down here on the Arbuckle uplift, that we have that cherty interval on the top of the Woodford, and only 6 miles to the south on the Caddo Anticline, the Woodford produced oil and gas naturally from vertical wells, because those cherty intervals were naturally fractured. Well, when we get into the Woodford, we'll compare some of the elements, and we're going to see evidence for authigenic silica in the Woodford. And those of you who've worked the Woodford know that, yeah, there's a lot of authigenic silica in the Woodford from radiolarians. But when we move away from the Woodford and start looking at some of these other rocks, and in particular the Caney, we don't see those cherty bands, those silica bands that you see in the Woodford. So there, we're looking for more subtle features, but we're still able to use X-ray fluorescence and compare some of the elements to find those intervals that have lower clay content and therefore more brittle and can be hydraulically stimulated. So here's the little Thermo Fisher Niton gun on some nice slabbed core. But we've looked at a number of shales, looked at the Woodford, of course, from the Arkoma, Anadarko, Ardmore, Marietta basins. I have a student who's actually looking at the Woodford right now up on the Cherokee platform. And we've looked at a number of other shales as well. But we look for concentrations of certain trace elements, and I'll show those again in the next couple of slides. And the ones that we're looking at in this study are what we call those terrigenous elements, elements that are coming into the depositional center, the basin here, in this case, from the land, from the continent, so to speak. And I'm presenting XRF results today, but they've been compared with other data sets, including X-ray diffraction. We have tight rock analysis, porosity and permeability, source rock analysis. And by integrating this data, we're getting confident that we can identify those reservoir and seal intervals. And then at the very end of the presentation, there's something that I'm still continuing to work on, is we have a sample set, bit cutting set, and we're going to compare that with a nearby core to see the relationship between the two and see if bit cutting XRF will work. So trace element proxies have all kinds of applications. And when I first started looking at trace elements, I was involved with people that were studying the Woodford, and we were looking for anoxic to euxenic conditions, and we were looking at those indicators that we have in very small concentrations, things like molybdenum, vanadium, uranium, nickel. For paleo productivity, we would look at copper, nickel, and zinc. And then if we were, in some later studies, we were looking for carbonate-rich intervals in some calcareous mudrocks in the Rocky Mountains, looking at the concentration of calcium, magnesium, strontium, and things like that. But today, we're going to hang out up here with the terrigenous elements. And we're going to look at aluminum, silicon, titanium, zirconium, potassium, and we're going to stay away from the rubidium and the thorium today and concentrate on these other elements. We have a set to use, and hopefully we can learn something from them. The diagram in the center here is borrowed from Wenatchee Valley College. And it's a simple diagram for an intro geology course that just shows in a generalized sense siliciclastic depositional systems and some of the depositional settings we can find. And I like the diagram because it shows where the sources of these terrigenous elements are coming from. We're interested in aluminum because we're looking at mainly aluminum silicate clay minerals. And I can say that because we're looking at a depositional setting that is not next to an orogenic belt. In other words, we're not looking at sediments that are rich in siliciclastic detritus that's coming off a granitic basement rocks that have been uplifted. So because of that, we can take a little bit of liberty with our aluminum and potassium and say they're principally coming from the aluminum's in clay minerals and the potassium's coming from clay minerals. Now, sure, some of it's probably coming from feldspar, but we're confident with the grain sizes that we have and the weathering that these rocks undergo, both the physical and chemical weathering. By the time it reaches these distal ends of these sediment dispersal systems, most of this aluminum is going to be coming from clay minerals, and the same for the potassium. The silicon's going to be in a detrital setting coming from detrital quartz, silt and sand that's being washed into the basin. The titanium is going to be with the quartz in the form of rutile. It's going to be associated with the silt primarily. And if we get some fine grained sand, it'll be associated with it as well. Zirconium, zircon grains are going to be associated with that quartz, silt, and sand. So here's an example from the Woodford Shale, and it's from Eli Rees's thesis from 2016. And we're looking at Woodford, and if I remember correctly, I believe this is Garvin County and down in the Scoop Trend. And over here on the right-hand panel, we have our gamma ray. This is just an image from a TIFF image. And we've colored in the P curve blue, and in this case, the neutron porosity is red, and you're going to find I'm inconsistent in my coloring. I'll try to help you through that. And the density porosity is in black, uncorrected density porosity. Now, I'm going to show a number of these diagrams today, but I want to bring your attention to these arrows at the base of the diagram. These arrows indicate increasing value. In some of the diagrams, we're probably not going to be able to see the values at the top up here. I mean, these the concentrations in weight percent. But we know that silicon, just based on the arrow, is increasing to the right. The same thing with the log curves. Our gamma ray is increasing to the right in this particular diagram, and it will change. The PE is increasing to the right, while the porosity is increasing to the left. So we'll start with the Woodford here. At the very top, it gets churny enough that PE is almost kissing that 2-line PE value of 2. But more importantly, we're seeing our neutron porosity and our density porosity touching each other. And remember, uncorrected density porosity, I can say with a great deal of confidence that this rock does not have 20% density porosity. It hasn't been corrected for organic matter. It hasn't been corrected if the well was drilled with an oil-based mud, and none of those corrections have been made. This is just as received, hasn't been corrected for grain density. This is just as received porosity from the well log suite. And then the top up here, and we'll take this interval where you actually have a little bit of neutron density crossover, if you want to call it that. In the Churdy interval, we see that titanium and aluminum are both decreasing, while our silicon is increasing. Now, if our titanium is coming in with detrital quartz, and our aluminum is coming in with detrital clay, and our silicon is coming in with detrital quartz and silt, these three curves should all be decreasing and increasing together, but they're not. We're seeing a separation, a decoupling of titanium from silicon, and that tells us that we have another source of silicon here than detrital quartz or silt, and we know what that source is, and we'll see pictures of it here in a bit. It's orthogenic silica coming from radiolarians. Now, let's jump down to the very bottom of this particular Woodford section. And we see we have high neutron porosity. It's separated by 1, 2, 3, 4, 5, 6 or so chart divisions from the density curve. It's telling us we have a high clay content. And what happens to our curves over here? We're seeing an increase in titanium. We're seeing an increase in aluminum, but we're seeing a decrease in our silicon related to quartz. So this bottom interval down here is a clay-rich interval, while the very top of this Woodford section is a really silica-rich Churdy interval. How do we know? Well, we have to look at the rocks, of course. We can do it with cuttings, but having core and thin section photomicrographs from cores, much easier to work with. Now, this is some of Eli's rock, and here we see some of that Woodford. You can see these smooth-looking silica-cemented bands. They have vertical fractures. Some are open, some are cemented, and then you see some thinner bands in here, and they're separated by these other gray colored intervals, which are more clay rich. But this is from the top of that particular core, and it's naturally fractured. And I've had more than one petroleum engineer tell me that in the Woodford, where they have these cemented natural fractures, they are weaknesses in the rock, and that they will reopen when they're hydraulically stimulated. Now, so I said that based on that decoupling of titanium and silicon, that this is autogenic silica. And when we look at the rock, we see the silica test from the radiolarians. And when we get into a silica-cemented band, we can still recognize a few of the tests in here, but they've been compacted and that silica's been mobilized and spread through the interval to generate this silica-cemented band, while the one right next to it, comparing across one of these boundaries, has a lot of clay in it. It has some isolated silt grains, but it's a dark clay-rich interval. And this is very typical of what we see in the Woodford in southern Oklahoma. Now we'll move down to that clay-rich interval. And one of the first things that we've learned about clay-rich intervals in this rock, Pennsylvanian shales, the Caney, the Sylvan, about any of these clay-rich shales, even though the core is stored in a climate-controlled environment, just normal climate-controlled air conditioning and heating, it's starting to delaminate. And we see this reaction to exposure to the atmosphere over and over. When we look at thin sections of these intervals, and this is a pretty neat little section of core. It's got some phosphate nodules in it. It has some marcasite or pyrite after burrows, and some clay-rich bands and a little more silty bands. Conodonts over here in the thin section photograph. Clay lenses, a lot of silt, quartz, and it's just a very different looking rock than the previous rock up in the Cherty zone. The radiolarians are rare to missing, and in this particular case, we're seeing different type of deposition, both at the core scale and at the thin section photomicrograph scale. So this is the most famous Woodford outcrop in the world. From picture up under the ledge there on the west side of I-35 in the southbound lane. We can see the phosphate nodules. You can see the chert beds. You can see the fracture pattern in the chert beds. This particular interval is really rich in chert, but there are some shaly laminated mudrock beds in separating these chert beds. Here's our field guide for comparison. And I have a Jerry McCaskill, most of you know Jerry. He gave me a section of a formation microimaging log from just 6 miles south of here on the Catawanic line. And you can, across this interval, you can pick up these features in that microimaging log. And for those of you who've been to the outcrop, you know that this is the upper part of the outcrop, close to those pre-Caney beds or pre-sycamore beds down there. They've sycamore along I-35. And the only other part of the Woodford that's actually exposed there is right down on the very top of the Hunton, at the Hunton-Woodford contact. And that more shaly part of the Woodford is not exposed because it weathered away and created a valley through there. And again, this field book is about 7 inches in height. Okay, so let's go to the Caney Shale. And this is a picture of some core from southern Oklahoma. I can tell you it's Ardmore Basin, and that's about it. And we see some of the same features. We see delamination in this interval. Here's a little more competent intervals. These light colored intervals are actually little thin carbonate beds composed of carbonate debris that was shed off the shelf, carried down by storms. Maybe some type of mass wasting deposits in some cases where they're thicker. But if you look at this little carbonate, you can see it's coarser grain towards the base and fines upward, and you start to think, well, that's maybe a mini Balma sequence or something if you want to get that technical. I want to bring your attention to the photomicrographs. This is a brachiopod fragment. A paleontologist told me it's a punctate brachiopod fragment, but wrapped around it, and you may not be able to see it, is illite. And this is a cross-polarized image. And this illite just wraps around here so nicely. It's platy. We have silt grains in here. We have a few carbonate grains. And then this plain polarized, well, is that one plain polarized? Yeah. Image here on top. We see these clay-rich intervals here, some silt-rich material, possibly agglutinated, benthic foram. It's hard to tell, but lots of silt in here scattered. Those little white dots are just silt scattered throughout. But there's so much clay. The clay is in between these silt grains, in some cases very fine sand, and so they're not touching. They're just kind of floating in this clay matrix, and it creates a rock that meets the introgeology definition of shale. Our introgeology definition of shale is a rock that breaks into these thin laminae or thin beds when it weathers. And this rock is trying to do that. It doesn't do it as well as those clay-rich intervals in the Woodford, but this delamination reflects that clay and silt content. So let's look at a different kind of rock. This is a core piece, about 1 foot in length. It's competent. It's not delaminating. You can see where the corner has been whacked off of it here with a hammer. Here's a separation along a bed up here, but it's a different looking rock. And when we get into the micro scale, we start to see more silt. We see more light colored material that's either going to be silt or in some cases carbonate cement. But it has more cement at the expense volumetrically of clay minerals. And what we don't see compared to the Woodford is we don't see radiolarians. Now, we feel like we've identified a radiolarian or two in the Caney photomicrographs, but you don't see the layers of radiolarians that we see in the Woodford. So, based on the limited core that we've seen, you don't see chert beds in the Caney. You don't see chert beds in the Caney and outcrop over on the Lawrence uplift. So it's a different kind of rock. It's a more complicated rock. It's more ductile generally overall. It's a more difficult rock to work with. Now, here's another type of rock we see in the Caney. And this one does show it's pretty competent. Okay, it looks good. It's not delaminating like the clay-rich intervals. This was cut with saw, but it does separate along the bedding. But it has abundant silt. Those white dots are little quartz silt. Mixed in with the silt is a lot of clay. And we see some quartz cement starting to develop in here. So this is a rock that is rich in both clay and silt. And it shows that the higher magnification shows that clay, mostly illite, is interspersed with the silt grains most of the time. But in some cases, we're seeing quartz to quartz contact, and we're seeing some brittleness starting to be imparted to this rock. And this will have an influence on the log characteristics and also on the elemental concentrations, which we'll see in a minute. So here we go. This is a section of Caney log. No depths, no locations, but this is about 100 feet, 100 feet represented by this arrow. And let's just start out with what is identified as a silica. And I probably should need to add carbonate-rich zone, because this zone right here is what we would consider a reservoir. Titanium is decreasing. The zirconium concentration is decreasing. The aluminum concentration is decreasing, while our silicon concentration is increasing. The same relationship that we saw in the Woodford, where we had chert bits, but we don't have chert bits in this rock. Let's look at this interval right below it, or the one right above it. Let's just take the one right above it. This is a clay-rich zone. Our titanium is increasing. Our zirconium is increasing. Our aluminum is increasing, but our silicon is decreasing. So this is an interval that has more clay at the expense of silicon. The one right below it does the same thing. And then we're going to jump down here and look at the interval, which was the last one I showed the photomicrograph for. This interval with all of this detrital silt and detrital clay. In this interval, our titanium is increasing, our zirconium is increasing, our aluminum is increasing, and so is our silicon. And we call this a detrital silica and clay rich zone. Now, what about productivity? Based on the limited number of Caney completions in southern Oklahoma, we know that this interval, or intervals like this with these characteristics, they work, they produce. This one, to my knowledge, and there may be people out there in the industry that know much more than I know there are a lot of people out there who know a lot more than I do, but it's about this specific interval. To my knowledge, it has not been tested. So let's look at our neutron and density curves over here. And this time I switched colors on you. The neutron is blue. The density, uncorrected density porosity is red. And they're both increasing to the left, while our resistivity is increasing to the right. In our reservoir interval, which has less clay, what we're calling the silica-rich zone, you'll notice that neutron porosity and the uncorrected density porosity are touching each other, almost to the point of trying to cross over. If we look at the clay-rich intervals above and below, notice the separation between the neutron and the uncorrected density curves. They're running away from each other. And in this case, from the limited number of logs that we've seen calibrated back to core, when those two separate, that's indicating high neutron porosity, high clay content, and those are more ductile, non-reservoir zones. While when those two curves approach each other, it's indicating we have less clay content, decreasing neutron porosity, and we're high resistivity, and that is a productive zone. Now, there's something else we have to consider. What about those thin carbonates? And here's one of those thin carbonate zones, and the titanium really drops off here. Zirconium drops off here. Aluminum bottoms out here, and so does silicon. It's just a very thin, few feet thick detrital carbonate in that basin. And when we get down to the bottom, you see the same relationship in another one of our carbonate zones. And when we look at our porosity, both porosities are very low. Resistivity is high. And this one up here, you see that neutron and density porosity, both are almost touching 0%. And the density, excuse me, the resistivity is quite high. Okay, all right, let's compare neutron porosity, aluminum concentration, and silicon. Kind of zooming in on an interval here. So here's a limestone. And this is not a limestone reservoir, by the way. It's reservoir right below it. But we see aluminum decreasing. Got to look at the arrows at the bottom again. Even I need to look down at the arrows. In this reservoir, our neutron porosity is decreasing, our aluminum is decreasing, and our silicon is increasing. Let's compare that to a non-reservoir interval. We have increasing neutron porosity, we have increasing aluminum concentration, and we have decreasing silicon, and probably in the form of silica of some form in weight percent. So we see this pattern repeated. If we go down to what we call that detrital clay and quartz-rich zone, we have increasing neutron porosity, increasing aluminum, and increasing silicon in the same interval. So it's a very different log response than we see up here in some of these reservoir intervals, or from what we see even in the ductile intervals. So we'll look at log curves again. We're going to look at neutron porosity, resistivity, and density porosity. Just focus in like, okay, so we only have a log here. Is this log telling us something that we've learned from our core? Here's a reservoir interval up here again. The same curves. Your neutron porosity and your density porosity are almost touching each other. We see the separation in the non-reservoir. Here's one of those thin limestones. Again, very low neutron and density porosity and high resistivity. And some of the other thinner reservoir intervals in here. Here's one here that's, you can see the neutron and the density porosity, uncorrected density porosity, trying to touch each other. And we see high resistivity. Some of the others aren't so obvious on the porosity side, but we know from some completions that some of these intervals like this have been successfully completed and produced. When we get back down to that detrital quartz and clay-rich interval, yeah, it's not showing us a distinct pattern. And on the neutron and density porosity side of the panel, and our resistivity is somewhere between what we call non-reservoir and what we consider reservoir. So will it work? Well, we'll learn that someday, I'm sure, if oil prices remain strong enough. Someone will try that one and we'll find that out. Now, let's add in some type rock analysis and some source rock analysis data. The first thing I want to point out on this panel is a silicon aluminum ratio. I've seen that used, and we developed one in this case for this particular area for the Caney, where we use an arbitrary value of something like 3 to indicate that if you have a higher silicon aluminum ratio than that, you're going to have what's colored in green. Yeah, green is for reservoir rock. And one of the things that's kind of interesting, and we see it right up here, is we see an increase in TOC, and we see an increase in permeability and an increase in porosity in this reservoir interval here. Another presentation of the log, we've added gamma ray, and we have porosity increasing to the left this time and resistivity still increasing to the right. And I've tried to make those resistivity threshold values easy for you to see. This is 100 ohm meters, and this one, the outer one here, is 1000 ohm meters. And this is something that seems apparent from what we've seen in this area for this interval, that the resistivity appears to be a pretty good indicator of reservoir. Now, that may not hold true if we start to get into really tight carbonate intervals. But in these mud rock intervals that are silty clay stones or clay siltstones for the most part, when we see that high resistivity, and then if that high resistivity is coupled with increasing gamma ray, which might be reflecting our TOC, our organic matter content, then I start thinking, well, we probably have some organic porosity in here, intra-organic porosity, and it's contributing to some of this better porosity and permeability we see in the permeability and the porosity curves in the middle of this figure. So how important is organic matter? Well, it looks like it may be as important in the Caney as it is in some areas in the Woodford, where a significant amount of that porosity and storage capacity in the Woodford, and now maybe so in the Caney, may be in organic matter, and it's something that needs to be looked at in more detail. And down at the bottom down here, fortunately, I have a carbonate interval that has very low porosity, very low permeability, and low TOC. And so it's we see some patterns that develop in using core calibrated logs that I think when we step away from core, if we see some of these wireline log characteristics, they're telling us some ways that we can identify reservoir and non-reservoir intervals. This is just a close-up of one of the reservoir intervals. And we have reservoir here with, these are in millidarcies, 0.0015 millidarcy rock. That's our best rock. And porosity here reaches 4%. And I might want to point this out again. If we look at our uncorrected density porosity over here at 13%, and our tight rock analysis porosity at 4%, it just shows you the importance of those density porosity corrections for the matrix density, for the type of drilling fluid. And again, this was a well-based mud, and also for the organic matter content. And of course, if we looked at the previous slide, we saw that organic matter increasing. The more that organic matter increases, the more that correction is going to be. But just things we have to keep in mind. And here in our non-reservoir, we see lower porosity compared to at least the reservoir above. It's pretty similar to the reservoir below. And I think that's important to note. Porosity, the true tight rock analysis porosity, I don't even call that true porosity, but better porosity, doesn't change that much across some of these intervals from what the reservoir interval to the non-reservoir interval. But the importance is the change, as I've said many times, in the clay content and how brittle these rocks are. So we may have porosity in this interval, but when we stimulate that well, we're not going to access those pores like we will in those brittle intervals. And let's see what the next one is here. Okay, so this is a close-up of that detrital interval. And the first thing to note that we don't have that silicon aluminum ratio that meets that threshold value that we've used to characterize some of these other reservoirs intervals. And we see some pretty good porosity here at 4%. We see some pretty decent permeability in this rock. Our neutron and density curves aren't trying to really go towards each other, but they're not separating either. And our resistivity, well, in certain intervals here, it's getting up close to 1,000 ohm meters, but overall it's between 100 probably and 200, 250 ohm meters across here. It's not like our reservoirs that have been proven where we're getting out there with that 800, 900 ohm meter rock. But I'm I'm anxious to see if this rock will work and produce commercially. Okay, let's zoom in and look at the microscopic level. Here's some backscatter element mapping, mineral mapping, and this is in the Caney. I'll start down here in the left side lower panel, showing this yellow-green color. And these are some images from a boss's work when he was down at the survey. And in this case, he chose this yellow-green color to represent aluminum. And aluminum, in this case, we're assuming is mostly from clay minerals. In the middle image here, the dark red, where the arrows are, the white arrows point to, those are quartz. The deeper colored red is still the silicon detected in the clay minerals. And clay minerals are alumina silicate minerals, as we all know. And up in the top left image, we have all this other stuff in gray, and our calcium is in this, I don't know, purple or magenta. I don't know what color that is. But there's not very much calcium in here, so probably not much calcite. There aren't a lot of silt grains in here, or maybe very fine grained sand, but there's a lot of clay in this non-reservoir interval where this sample was taken. Let's jump over to the brittle reservoir images on the right. And let's start down at the bottom with our aluminum. And you can see there's just a lot less aluminum in this reservoir sample. And these other materials are, if we see here in this middle image, that again, we have bright red quartz, and you can see that some of these quartz grains are touching, which is always good. And when we go up to the calcium, we see a lot more calcium in here. So there's probably a lot more calcite cement in between these detrital quartz grains. And we're giving this rock rigidity. We're making this rock more brittle. And the mechanical properties measurements that done here in our shop with the hardness tester, done on the core with the engineering folks have done both at Pittsburgh and at OSU. There's nice correlations between the elements, these more brittle minerals, and increased hardness, brittleness, mechanical properties, good mechanical properties. Okay. Well, what happens when we throw cuttings into the mix? So here are some cuttings from a nearby well. And let's start with the reservoir. Now, first I need to explain, you'll notice that you're not going to see a perfect alignment of core depth to cutting depth. That's because they're not depth corrected. So your cutting depths, because of lag time to get cuttings back to the surface, and we all know that, they're going to be a little deeper. But let's start with a reservoir. And we'll start with the core with lower titanium. Look at our titanium curve from our bit cuttings. Again, it's decreasing across the same interval. They overlap some, but also continuous below it. The same thing for zirconium. The decreasing in core, decreasing in cuttings. Aluminum, decreasing core, it's decreasing in cuttings. And our silicon is increasing. And over here in our cuttings, we see it represented a little differently. But again, we're seeing an increase in silicon in the reservoir interval. We see just the opposite in our non-reservoir interval. Titanium's increases, relatively speaking, to the reservoir in the cuttings. Zirconium does the same thing in the cuttings that the core does. The aluminum does exactly the same thing. And we get over here and look at our silicon, it decreases from our reservoir to the non-reservoir interval. Now, the limestone at the top of this particular display. This one really surprised me. I did not expect to see the limestone in the cuttings, just because it's thin And no, wasn't there when the cuttings were caught. But apparently the roughnecks, whoever the sample catcher was catching things on time when they were supposed to. And as a result, we got a nice set of drill cuttings. And in our cuttings, we see our titanium decreasing where it should. Our zirconium's decreasing in these couple of these samples from the cuttings. Our silicon drops off in here because it's a limestone. And that really surprised me. I did not expect to see that. Now, in here, where we had some of those thinner reservoir intervals, they don't stand out. Would they on cuttings caught on a 5-foot depth interval? I don't know. I can tease some of them out, but it really takes imagination to do that. But when we get down to that thicker interval, that detrital quartz and clay rich interval, we see our titanium increasing with the core values. We see the zirconium increasing. Yeah, it's dropped down a little bit because of the lag issue. We see the aluminum increasing, and we see the silicon increasing. So the jury is still out on cuttings to me. I want to look at more cuttings sets and compare them to see, I'm pretty confident that if you have a reservoir or a non-reservoir interval that's, 25, 30 feet thick, you're going to see it in the cuttings. But it's those thinner ones that I would also like to see if we can tease those out of the cuttings data, if we have good cuttings caught promptly at the right time, and of course we need great mud systems to do that as well. So the takeaway, how are we doing on time? Oh, I've got to get finished here. Okay. Reservoirs and non-reservoirs, based on the work that we've done, they have different elemental signatures, we can call them geochemical signatures. And our reservoirs have less aluminum because they have less clay and less potassium, while our non-reservoirs are going to have higher concentrations of aluminum, potassium, zirconium, titanium, and along with lower silicon. So reservoirs, from what we've observed, can have higher uncorrected density porosity and have lower neutron porosity because of that lower clay content, causing that neutron and uncorrected density curves to converge. While in contrast, our non-reservoirs have high neutron porosity. It separates from the density porosity because of that high clay content. And I think this is important. The higher resistivity in those reservoirs, I think that's an important characteristic. And if I'm looking at old logs, we may be looking at, may even be before pre-density curve logs, certainly before pre-neutron curve or curves. And I see those zones that have high resistivity. And if they're coupled with high gamma ray, I'm thinking automatically high organic matter content. May not be, but I'm thinking that way, leaning that way. And low clay bound water, and I'm thinking that's probably a reservoir interval. That's something that I like to use the term romantic. We need to explore that further. So when we see increased calcium or increased silicon at the expense of clay minerals, that's good news. It makes the rock more brittle. And the great thing about it is, and this, if we have the adequate well control, and you're in an area where they drilled through some of these organic rich mud rocks to get to deeper, maybe Silurian, Devonian, or Simpson group, Hutton, Simpson group areas in Oklahoma, may apply to different intervals in other basins, but using resistivity, if we don't have the other curves, but certainly resistivity with gamma ray, you can map these subunits, and where we have adequate well data, we've successfully mapped them. And they thicken and thin just like any other reservoir intervals do in sedimentary environments. They're isolated with ductile beds on either side. And now that we're in this transition mode, now we're out there looking for oil and gas reservoirs. But if when these things are depleted, we have some well delineated compartments that we might want to store fluids in the subsurface when we're into the subsurface fluid management, as I like to say. And I think that we're confident that XRF was effective in identifying key elemental proxies. And at least with the rocks that we've worked with, we can identify reservoir, non-reservoir intervals. So here are some of the references. And I finished with this slide. This is just a Chattanooga shale outcrop over in Delaware County on the flanks of the Ozark uplift, where you can see the Compton limestone, the Chattanooga Woodford Shale. And I like this because the Woodford is low enough clay content here. Far from southern Oklahoma, we don't have chert beds up here, don't have a lot of phosphate. But they built this road right on the Woodford, and it made a good road. Then now there's some gravel mixed in with it, but it's mostly just Woodford Shale, and it has low enough clay content to make a decent unpaved road. Okay, that's it. I welcome questions.
Now, this is great. I'm really, I mean, I love the Caney stuff you're saying about the Caney. And I have a question about that.
Okay.
Okay, so in your opinion, the Caney is, obviously really complicated and laterally heterogeneous in a way that, and discontinuous in a way that the Woodford is, I mean, it's not as homogeneous laterally or continuous laterally as the Woodford. So what are the implications for the reservoir size and ultimately for like migration pathways, et cetera?
Oh, that's a really good question. And that I hadn't really thought about that, what you just said. Yeah, the Cherty zone on top of the Woodford can be mapped literally for tens of kilometers and miles in the sedimentary basins. While the Caney is, as you said, a lot more localized, the reservoirs are.
Mm-hmm.
And maybe they're more isolated. Maybe they're, well, we know, therefore, yeah, I can say based on production information that I've seen, the Caney is not the Woodford. You're not going to get Woodford type production numbers from the Caney completions that I've seen. But that doesn't prevent them from being economic at the right oil price and gas price.
Mm-hmm.
So I believe, and I don't have source rock data on the Caney. I'm sure there are people out there that do, but certainly the Caney is organic rich enough that it could self-source if it needed to, but gosh, it's so close. It's so close to the Woodford with, depending on the facies changes with the sycamore and the Caney, it could be sourced from both if there are any through-going fractures. So I'm not worried about the sourcing, but the reservoirs and ultimately the production for the Caney, from what I've seen thus far, and again, for those of you who've worked the Caney, there aren't a lot of Caney completions out there, and not a lot of Caney data floating around. It's not the Woodford, but it may be good enough to develop as a play. Well, it is in certain areas. They've already proven that.
Well, I've been super, super interested in the recent Colibri press releases where they are in the Tishomingo field. And I just, it sort of surprises me that the IPs are not what you get in Woodford completions. I mean, they're like 700 or 800 barrels of liquids a day. Then I don't know what that's based on. an hour flow or but
Exactly.
but it's encouraging because it kind of gives us another target out there because and this is an area where there could be multiple pays.
Yeah, and it's also in an area where the Caney is present in a lot of these areas where their Woodford's already producing. Now,
Mm-hmm.
I don't know how the leases are written. I don't know if those Woodford wells are holding Caney interval. But I mean, at least the infrastructure is there.
It's
You're
a
already
really
there with your
yeah.
infrastructure. So it might be a less expensive uphole completion. But yeah, I'm always encouraged, and I'm like you, I like to see those 30-day or 60-day numbers out there, but there are some Caney wells down there that have some pretty impressive numbers.
Yeah. Yeah, I'm with you. And the thing is too, is that if the leases aren't if it's not holding, if they're only zone only, which I kind of doubt, but I mean, if it's anything above the Woodford, they could, but even if it isn't, they could still have some kind of arrangement to use the same pads and the same infrastructure and all that.
Yeah. Dwayne, you can ask me a red fork question if you want to. He's not going to.
And Dwayne's being shy.
Yeah.
Yeah, this is a really, really great presentation, and I learned a lot. I mean, this is one of my favorites, one of the best I've seen. And so I am really grateful and appreciative.
Well, thank you.
We'll put this on the web and we'll make it available. So I'll
Yeah,
send it email to everybody who is signed up and they'll get a link to it.
yeah. I've been invited to take it down to Fort Smith and Ardmore, so
Oh,
that will be fun.
I'm hoping to have some people from Colibri and maybe well, I was maybe you. I'd like to maybe just focus in on the Caney, and just have kind of a round table, and then just kind of like speculate on the reservoir architecture, continuity, potential, because this is the first time in a long time I've seen some like reasonable results for sort of new shales. But yeah, I'd like to do a webinar and also have a panel at Your Tech in Houston in June.
Yeah. All right, anybody else?
Last chance.
Okay, well, I've enjoyed it.
Thank you, Jim. That was wonderful.
Okay, you all have a good day.
Thank you.
All right, everybody